Hi and welcome everybody to the lecture titled Orthogonal Frequency Division Multiplexing, a transmission technique that's used in Wi-Fi, LTE, digital video broadcast, WiMAX, and even 5G. Such a great technology being implemented in many standards, in many wireless technologies deserve to be understood, deserve to be learned, and deserve the attention, and it motivates us also in a way or another to build the new technologies built on top of it so that it can be adopted in the future of wireless technologies. So why do we study OFDM and what's the importance of this waveform called OFDM? First of all, it provides effective usage of the bandwidth. For example, in the old days, we used to use frequency division multiplexing where you send your data over each subcarrier and there are guards between them. This is wastage of resources. In OFDM, luckily, we can squeeze the subcarriers and avoid these guards so that you can use the spectrum in a more effective and efficient manner. Fundamentally, the waveform is well suited for high bitrate applications, and this is why we like OFDM. Because in the old days, when we moved from 2G to 3G with the technology called FDMA, one of the key problems was equalization. Equalization in the time domain is very hectic, very difficult, tedious process, complex, consume resources, not easy. To avoid that, we came up with OFDM, and OFDM with adding cyclic prefix as guard interval, it can help make the equalization process much simpler and easier and user-friendly. It's robust against narrowband interference. It enables simple frequency domain equalization, just multiplication process, lower complexity than deconvolution in time domain, easy handling of intersymbol interference. Not only this, but also time recovery is very straightforward in OFDM. Good support for highly variable bitrate application, easily managing multiple axis interference by activating and deactivating the subcarriers of the OFDM. It enables dynamic channel allocation based on the requirements of the application. If your application is using video, you can just increase the number of subcarriers to serve it. If your application is using text, just reduce the number of subcarriers or the number of slots. Flat channel on subcarriers, you don't experience this frequency selective channel per each subcarrier. Each subcarrier experiences flat fading, which means the equalization and getting rid of this flat fading channel is very easy, simple division. It can be easily implemented and integrated with MIMO systems. So we call it MIMO friendly. Why do we need MIMO? Because MIMO is the only way that we have to improve the spectral efficiency of our systems. Now, in an efficient manner, I mean. But, as it usually happens, anything that has so many advantages, on the other side, it has so many disadvantages. And these disadvantages, actually, they motivate the research on this domain. And our goal is to reduce these advantages or remove them, reduce their effects, to get the best of the two worlds, maximum advantages with minimal disadvantages. One of the key problems of OFDM, it's basically the sensitivity to Doppler and mobility. When the car is moving with a very high speed, OFDM is very sensitive to this. Because if there is any non-orthogonality between the subcarriers, you will have disastrous interference and your data will not be received reliably. Synchronization requirements are much more strict, requires more complex algorithm for time frequency synchronization. It causes out-of-band emission leakage. Why out-of-band emission leakage? Because we have sync. OFDM, the shape of the OFDM pulse or carrier in frequency domain is sync. Sync is coming from rect in time. the rect is confined in time means in frequency it will be spreading. It has side loops, and these side loops, they oscillate to infinity. Very bad. We don't want this to happen usually. And peak to average power ratio. Peak to average power ratio is the maximum amplitude that your signal can go over the average one. We want it to be low because power amplifiers usually work on linear region. So to make sure that we can amplify our signal as much as we can, we want to be away from that saturation region. So the more you reduce this peak to average power ratio, the more you have flexibility to increase the output power of your transmit signal and amplify it in an efficient manner. Not put too much power and don't get output amplified power. Large signal peaks require better higher power amplifiers. Amplifier cost, and when you use this, when the peak to average power ratio is low, the cost of the power amplifier becomes not that much. So basically, before we understand the OFDM list, let's understand the basic principle of TDMA with FDMA principle. So basically, you have time and the frequency. We call these are the resources. This is where you allocate your user. You say user 1 is here using the frequency in purple and the time from this duration to this duration. So basically TDM with FDM, you divide your area, your land, which is the resource, into pieces. And these pieces you assign it to users based on their requirements. Based on the requirements, how much data rate you need. If you need too much, we assign too many pieces for you. If you need little, we assign little. Basically, we divide the frequency and time to pieces, 10 slots, and we assign them to users based on or applications based on the requirements. And this, the y-axis is power. So it's a 3D representation. In CDM, code division multiple axis principle, over the same time, at the same frequency, you have multiple signals on top of each other. How do you separate them from each other? Using orthogonal codes. And OFDM is basically using time, frequency, and carriers, but the difference between this and this is the fact that the carriers are overlapping with each other. Overlapping means going inside each other, but they are not interfering. This is the beauty, the feature of OFDM. We call the yellow one time slots in time domain, and in the frequency domain we call them carriers or subcarriers. Data is transmitted in parallel on multiple carriers that overlap in frequency. So conventional multi-carrier techniques is FDM, frequency division multiplexing. As you can see here, carrier 1, carrier 2 with channel 1, channel 2, channel 3, channel 4. So for transmitting, let's say how many symbols these? 10 symbols. For transmitting 10 symbols, you require 10 subcarriers separated with guards. These are guards to protect it from the interference. With OFDM, what's the beauty of OFDM? You can transmit 10 symbols within half the bandwidth. Why? Because you squeeze them, you overlap, they overlap with each other, but they don't interfere. You can get the symbols right. So this is the old FDM and this is the OFDM. So basically OFDM, this is the first feature of OFDM. It utilizes the spectrum in a more efficient manner. And these are the subcarriers of OFDM that carry the data. And when they add up to each other, the overall waveform you get is the one in black. You see this. You don't see these ones in different colors. because these are separated, but signals usually add up to each other. This is for visualization, for understanding how OFDM works. But basically, you get your black signal once you transmit your data using OFDM. Each carrier is modulated. Each carrier here is carrying BPSK or QPSK symbol, the one you studied in wireless in the previous courses. A frequency response for each carrier is sync, as you can see, sync with and these side loops. This is the main loop and these side loops. Frequency responses of the carriers overlap at zero crossing, avoiding inter-carrier interference. At these points, you have zero contribution from all the other carriers, meaning at this point, all the carriers are zero, except one. For example, at this point, all of them are zero except the purple. At this point, all of them are zero except the blue. At this point, this means that they are not interfering with the main subcarrier, yes? With the main loop subcarrier. Since they are not interfering, you can transmit and receive your data reliably. How do you generate them? Basically, the sync function is the Fourier transform of a rect. But how do you shift the frequency? At which location it's residing? How do you determine in which location, on which frequency your sync is setting, your sync function? How do you determine that? Based on the frequency of the sign. For example, the first sign here, when you take the Fourier transform of the first sign with sync, you get sync. Don't think of this as column, think of it as sync, but we didn't draw it like sync because it will be much easier to see the position. This sinusoidal signal, yes, with certain carrier frequency. When you take the Fourier transform of this is not infinity sinusoidal, limited within a box. So when you take the Fourier transform of a box, you get sync. And the frequency, how fast this carrier moves and oscillates, determine the position. When you increase the oscillation, when you increase the frequency, means you have many oscillations, it completes the cycles within the same, too many cycles within the same duration, you get your sync shifted at a different position in the frequency. See, when you take the Fourier transform of this, you get the same signal sync, but at a different frequency. When you increase the frequency more, means more oscillation. You get again sync, but a different frequency. When you increase more, you will get sync at a different frequency. So in time domain, when you sum all these up together, you get this random signal in time. But in frequency, it's like this. You sum them. This is alone, this is alone, this is alone, this is alone. Each one has its own band. And you can do this for the real part of your transmission and complex part, because as we know, communication system use real and complex. So you do this with each part, and at the end of the day, you get your OFDM signal. To maintain orthogonality between the OFDM subcarrier, what do we do? We make sure that delta F, the spacing between the carriers, the spacing is equal to 1 over the symbol duration. Where is the symbol duration? This is T, the symbol duration of one OFDM. 1 over T is equal to the subcarrier spacing. If endpoint IDFT or FFT, which is the fast Fourier transform, is used, then what's the total bandwidth? If the size of the FFT is n, then what's the bandwidth of your OFDM signal? It's n multiplied by delta F, which is the total bandwidth. Symbol duration after CB addition. Now you don't have only the duration of your symbol, but also you have the duration of the CB. This CB, we use it to protect the signal from multipath and interference coming from other symbols. Mathematically, how do you write the mathematical model of your system? You have your channel, and you have your signal, and you have the noise. Noise is added to your signal, and this is your received signal. K represents the carrier, and N represents the time, symbol in time. Nth tone for the kth OFDM block. So here is using the opposite. N represents the carrier, the tone, and K represents the OFDM symbol, block or symbol. And this is the basic block diagram of an OFDM. You have your input bits. You perform channel coding, interleaving, symbol mapping, which is modulation. Then OFDM modulation, I50, A50. You add guard interval, and you have two branches after modulation, real and the quadrature. And you send over the channel. This is the shape of your OFDM signal when you see it in the spectrum analyzer, in the hardware device, the red one. And this shows the visualization in time domain. And the blue part is the CB. And you transmit over the channel, and the receiver performs the opposite. Signals sent through wireless channels encounter one or more of the following distortions. After you send your signal through the channel, it gets affected by the following distortions. One, noise, additive white Gaussian noise. Second, the frequency and phase shift or offset, timing offset, delay spread, fading, co-channel interference, nonlinear distortion, and impulse noise. All these are impairments affecting your OFDM transmission, and you need somehow to design techniques that can remove and eliminate its effect. This is basically the main points related to OFDM waveform. Now, little by little, we can see the advantage of OFDM in reality. For example, how is OFDM robust against narrowband interference? If someone asks you, how you tell us that it's robust against narrowband interference, how is it? If someone is interfering with my communication and sending signal over this band to harm me so that I don't receive my signal, what do? You just deactivate these subcarriers, you don't transmit over them. And by doing so, you avoid the interference. OFDM in broadcast, why is it useful and good? Because in broadcast, you have long distance, and the signal is reflected from many buildings, many objects, and you receive long delay spread. Long delay spread is disastrous if you were to equalize in time domain. But OFDM, all these many tabs, if you design your OFDM properly, you will collect them within the CB duration. They will fall down within the CB duration. Since they are within the CB duration, you will not get any interference from them. And that's why we use it for digital video broadcast. Now, we always want to make sure that OFDM subcarriers are orthogonal. To maintain orthogonality, how do you check orthogonality in math? You take the first signal, take the second signal, conjugate, multiply with each other, basically get the dot product. If the dot product is 0, means orthogonal. So if you take this signal, the blue one and the red one, and perform this mathematical operation, you must get 0. Mathematically, this red-blue signal is this, e to j2 by fpt. Basically, 1 multiplied by this. 1 represents the rect in time, and the e to j represents the shift in frequency. So you get sync after the 4. And the same here, you get sync, but at a different shifted frequency. When you multiply them with each other and take the integration, you get 0. And this is your OFDM symbol before the channel. You transmit it. This is the channel. It gets convolved with the channel. After the channel at the receiver, this is how the channel affects your transmitted symbol. We call this after the dashed line here, we call it interference, inter-symbol interference caused by the channel. To avoid that, if you don't put protection guard here, you will get interference from the other adjacent symbols. To avoid that, what do? You put CB, you put here guards, remove guards, so that you leave some duration for the dispersion and you don't touch the other ones. You can do this by zero padding, you are not transmitting anything, or by adding CB. As you can see in this figure, by adding CB, you avoid the interference coming from the delay spread of the channel. So basically, this is the key feature and key merit of OFDM. It's robust against multipath fading. It's robust against interference coming due to delay spread. So I hope you review these at home, review these slides and read them carefully. And if you have any questions or this, you can ask them next lecture. And for now, we stop here and we continue next lecture. Thank you very much.